draw some diagrams corresponding to these vertices. This is set to notation. So this I was going to denote by curly lines like blue ones. So that's, well, I don't know, it doesn't matter, but A, B, C. And this, let me denote that by a curly line. Maybe to be consistent, I should put it downstairs. So a double line for the complex indices, because it's basically some kind of bifundamental representation. And there's an arrow. And let me not worry about the direction of the arrow, because I'm just going to get confused. And here, we basically have three complex representations. Something like that. No, we should go something like that. Let me see. That's probably wrong. So that's supposed to be alpha, so it's supposed to be the same as this guy. Okay, that's fine. And then we just reverse all the arrows. Right, so that's my three kind of interactions, right? And then I need to consider all the particular relations that this color coefficient, color structures, color tensors satisfy. Well, the first one is the obvious one, which is just a Jacobi identity. And I'm not going to draw the f's, I'm just going to do it diagrammatically. So that's the ordinary Jacobi identity. Then there's a commutation identity. And there's some arrows, let me not worry about the arrows. So that's the commutation identity. But then there's three more identities. So in particular, you can have, let's say that you have one of these Clebsch-Gordan coefficients, and then you attach a gluon to it. So I can attach a gluon here, or I can attach a gluon over here, maybe, on this side. And well, draw it like that. That looks a bit weird, but attach it there. So it's basically the same structure. There's one more. Let's see. So now, if you only have these Clebsch-Gordan coefficients, you're going to have this structure. But now let me put some arrows to make it clear. So if you have three incoming and one outgoing, then you're in this situation. But then there's the last identity, which maybe is the most interesting one. and well, let me just call it alpha, beta, alpha, beta, alpha, beta, and then subtract alpha goes to beta. And this is equal to this diagram. So this is a 7-term identity. And that comes back to my point that sometimes called kinematic duality is not just 3-term identities. Sometimes it could be other types of identities, like a 7-term identity. That said, it turns out if you fix these external indices to be some particular value, this always collapses down to 3 terms, or less. It could be less than 3 terms, but never more than 3 terms for specific values of alpha, beta, gamma, and delta. So basically, these are the type of color identities in spontaneously broken super Yang-Mills. And now we want to consider that this is the algebra that we want for the numerators. And it's basically trivial for this dimensionally reduced theory. And you can ask me later why it's trivial, or maybe ask me now why it's trivial. But what I want to do is I want to import this kind of structure to our other theory, which is this Yang-Mills coupled to phi cubes theory. So just to save me some time, I've written down this Yang-Mills plus phi cube theory up there in the white. And this was basically written down last summer. So it's basically Yang-Mills, and then there's covariant derivative for the scalar. The scalar has 2 indices, so it's bi-adjoint. There's a phi cube coupling. Lambda is dimensionful. G is dimensionless in 4 dimensions. This Lagrange can be considered in any dimension, but if you're in 4 dimensions, lambda is a dimensional parameter, has dimensional mass. And then there's ordinary phi 4 interaction. It's a pretty straightforward theory, although there's many indices, but it's pretty straightforward. What we want to do is we want to break this theory, and we want to only break the scalar sector, or this capital F. So there's a capital F ABC, which is the structured content of some global group, and we want to break it. So how do we do that? Oh, I think I forgot to say something here. Let me backtrack. Yes. I want to say something about the Yang-Mills, about the masses, the type of masses generated here. So let me just erase this part. So in this notation, with this F's here, and also let me say one more thing. If you have this SUN and 1 times SUN2 times U1, this means that there's a special U1 part, and this is basically it's the piece which lives both in this corner here and this corner here, and it came from the Higgs field originally. But that field is special, so we're going to call the generator of that C0. That's a special direction in the gauge group. And now we can write down the masses, or the mass matrix of this spontaneously broken super Yang-Mills. It's basically just F0 alpha beta. So it's basically this structure constant here, but you plug in 0 for this entry. And then you need something dimensionful, so let's call it V. And then you need some coupling, and maybe you need an I. So that's basically the mass matrix. And this basically means that there are certain particles which have a non-zero structure constant here, and they're going to become massive. And it's convenient to complexify them. So let me say that we're going to take our gauge field, which originally had this capital index, and we're going to break it down into the surviving gauge field, and then two W's, which are complex conjugates of each other. And what's going to happen here, that if you have properly diagonalized it, this is going to have mass 0, of course. This is a gluon. This is going to have mass alpha. If you diagonalize this matrix, there's going to be m alpha there. And this is going to have minus m alpha. So, so now, and the same thing can be done with the scalars. If you have a scalar phi a hat, this also breaks down in the same way. And well, I run out of space, so let me not dwell on that. So now I want to consider the other theory and do the same thing there. But I don't want to make the gluons massive, and that's the reason why I'm only breaking this global group. How much time? 5 minutes. So basically, I want to take my scalars, and let's call them capital A, and this is the global group, and this is the gauge group. So this is some, say, SU and C, and this index here is just some SU, I don't know, let's call it NK, because this index is actually part of the kinematical algebra. So I'm going to break this up into 3 pieces. So I want to keep the surviving massless field, and let's call it phi a hat, and then we have 2 complex fields, which are going to use curly phi, and then alpha a hat, and then complex conjugate alpha a hat. So it's completely mimicking the decomposition that I did here, but now it's only for the scalars, not for the gluons. Okay, so that's basically a decomposition. So you can just plug in the decomposition in here and see what you get. But it's not sufficient to actually break the symmetry, of course, because that would just writing the symmetry non-manifested. You actually have to introduce a mass term in order to have a symmetry breaking. And the mass term is not going to be sufficient. So we're going to add symmetry breaking terms. And this is for this symmetry here, SUNK. Such that 2 properties hold. The 2 properties that's going to hold is that if you take mass to be 0, then we recover the unbroken theory. And the second property that we want to hold is that color kinematics duality has to be satisfied or obeyed. And what I mean by color kinematics duality, I mean exactly these type of identities that I've written down here. We need those to hold for this theory. And, okay, and by analogy to the spontaneously broken super Yang-Mills, you know that what you should add is basically you should add a quartic term, you should add a quadratic term, which is the mass term, and then you might have to add a cubic term, and that's exactly what we're going to add. So the mass term is not so hard to imagine, so it's basically just going to be m phi, and you can put your indices there. Oh, let me put some indices, and then a hat, that. So that's the mass And now we want to pick a particular mass. So by analogy, how it worked here, we're going to say that the mass matrix is basically proportional to the structure constant here, capital F, after you have decomposed it into some complex representation. So it's basically F0 alpha beta. And we need something dimensionful, but luckily we already have something dimensionful here, lambda. So we just put lambda here. But there's no reason why this lambda, why this scale should be the same as that scale. So then let's put another number here, which is a real number. And then you might want to put an I here. And in fact, to get good normalization, you actually want to put the 1/2 as a that gives canonical normalization later on. So that's the first term, which is the mass term. That's basically, I mean, you know you need to have a mass term. I can pick it anyway. That's a convenient way to pick it. But the other term is highly non-trivial. So it's going to be a cubic term. So it's basically going to be proportional to ABC, if ABC, and it's going to be proportional to this structure constant again. And therefore it's going to be proportional to this phi 0 var phi, with some indices alpha, beta, and then A, B, C. But there is there's a coefficient here. Well, first of all, we know it has to be dimensional, so let's put lambda here. But then it could be a numerical coefficient. It turns out that the correct numerical coefficient that you can determine using color kinematics duality is the following. It's the square root of 1 plus rho squared. So that's what you need. Okay, and then I've written down the Lagrangian here. It's probably not readable, but it's quite a mess. But it's mostly quite a mess because of this decomposition here. So as soon as you decompose something, you break the symmetry, of course you're going to get a big mess. Where are the terms? So that here's, let's see, where's my mass term? Here's my mass term. And here is my basically shifted cubic interaction. And now I introduced a delta here. Which is basically it's basically a square root of 1 plus rho squared minus 1 as an identity matrix basically here. So it's just you shifted it, and the effect that it has is that it should be delta A0 delta B0. So it only has an effect for this 0 direction here.
So that mass term in the middle is really square. That n squared.
First line.
Yeah, the first line.
This one?
Above.
Oh, sorry, here, yeah, that's a square. Thanks, yeah. This is not a square, but that's a square. Okay, good, yeah. So this are basically the two terms you need to add to this Lagrangian. And then after you've done that and decomposed it, you get all of these extra terms. So you have to add this and add that. But anyhow, so now, basically done. Now I have two Lagrangians. I have my spontaneously broken super Yang-Mills, and I have my explicitly broken Yang-Mills phi cube, including all of these terms. And now I can do a double copy schematically. So GR plus broken Yang-Mills is equal to schematically this object here. So Ni super Yang-Mills, where broken Yang-Mills, the gauge symmetry, and then Yang-Mills plus phi cube over di. And this denominators now have a mass term, or they could have masses because it's broken. And that's it. So we check this. checked it at maybe not so impressively, but 3 points and 4 points and one tree level, and then one loop, 4 point. And we checked it against the explicit supergravity Lagrangian that you get from n equals 2 Yang-Mills-Einstein supergravity, and which is very easy. Oh, this is a very good theory to check against, not because it's simple, but because it's actually uniquely specified by cubic coupling. So as long as you have completed your 3-point amplitude, you basically know what this cubic coupling is. And then if everything is consistent, it should carry on to higher multiplicity or higher loops. And we did the 4-point check just to check that it indeed works out. But this story is more general. So as I said, this applies also to n equals 4 and to n equals 0. Although I should say that n equals 4 is actually, as far as we know, n equals 4 spontaneously broken Yang-Mills-Einstein supergravity with n equals 4 has not been written down anywhere in the literature. So yeah. Anyhow, so with that, let me end.
Okay. Thanks. So any questions? So if I want to do n equals 4,
Yeah.
so do I just add extra symmetries and
N equals 4, Yang-Mills-Einstein supergravity?
yeah? I mean, even though I don't have the
Yeah, then you just use n equals 4 super Yang-Mills.
yeah,
Yeah, that's all.
but it deforms on the other side.
Oh, then it's the same. It's the same.
Exactly, it is calculated.
Yeah. So this side, well, I guess I erased the equation, but this Lagrangian is bosonic, and you cannot make it supersymmetric because of the cubic coupling. So, but the other side you can make supersymmetric. Yeah. So there's an upper bound. You can have at most n equals 4.
For measure W based on W boson scattering, do you just add do you just calculate from diagram for the Armstrong lake?
Sorry, can you say anything?
Oh, so for that massive W boson scattering,
Yeah.
do you just calculate the Armstrong lake from diagram, or how do you treat bubble? How do you treat bubble Armstrong lake?
Bubbles.
Bubbles. Yeah.
Yeah, that's a good question. So the particular, yeah. I mean, for this theory, sort of, it's not so difficult to do it, because this is basically just a massless theory in higher dimensions. But for this Yang-Mills-Einstein cube theory, that's of course an open problem, unless you have the Lagrange. Well, that's the thing. So if you have the Lagrangian, which we have, you only need to impose polar kinematic duality on one side, and then you get the other side free. So in principle, you can just follow this Lagrangian, even though you cannot put it on a polar kinematic satisfying form necessarily in the bosonic case, where you have external tadpoles or bubbles. So that problem, it's a problem, but it can be circumvented. Yeah.
Okay. If there's no more questions, thank you again. Okay, so
I have something more to say.
okay.
Yeah. So okay. Yeah. So maybe one thing I want to say is that most of you maybe already know Amplitudes is going to be in Amplitudes 2016 is going to be in Nordita. So let me just put that here as a reminder. That's Nordita. Stockholm. And it's July 4 to 8. And one one more thing is that there's going to be a program as well. And this is something that sort of accidentally fell on us because there was cancellation, last minute cancellation just 2 weeks ago. So this is aspects of amplitudes. And this is also at Norbita. And the date that was assigned to us, we did not pick them, is June 13 to July 2, which is convenient for us because it's right before Amplitudes, but there's certain conflicts which I'm aware of with other programs. But anyhow, there's going to be 3 weeks of I think very nice activities and a very nice summer. And then maybe I should say something about Einan's conference in 2017. So Amplitudes 2017 is going to be at Edinburgh, Scotland, and what's the date again?
It's the 10th of July.
10 to whatever, 14 maybe? Okay, so that's all I had to say about this, and maybe I should say something on behalf of all the speakers and participants. I want to thank the organizers for putting together a really nice conference here, and
I think we should especially thank Zaro for really organizing.
But also thank Yutin and all the collaborators together.
And really the speakers, because you guys did the traveling. I just put the schedule here. Thanks for it. Thanks for it. So everybody survived, I guess, so we'll move on to the survive dinner. So, but before we do that, maybe we can all take a picture for all the survivors so we get all this stuff up for the fun.